Hello everybody and welcome back to our um, Automaton for Formal Languages class. This is the Unit 4 in which we will do three things. We will start or rather resume our journey of learning about finite automaton, their powers and limitations as computational devices. And then we'll formally define computation and start working with this model and definition to design finite automata to do really cool things. And then we'll see how we can actually expand on the idea and this formalism by looking at and defining regular operations. And then we'll start showing some certain properties of these regular operations on regular languages, and then we'll hit a wall. That will be a segue to our next unit. So bear with me, and let's go and start working on the um, the work. So if you remember from last unit, at the end of the last unit, I gave you all a do-it-yourself assignment to work on, and that was basically the last automata we designed, or rather we looked at last time. The last example of the automata that was really a nice little tool in that it had three states and it was able to count and add the symbols values that it has seen so far, and then decide whether that sum so far is a multiple of 3 or not. And then my assignment for you all was to expand on this idea and make that, or rather generalize that example and that automata, to use the same symbol alphabets and then try to see whether the sum of these symbols that it had seen so far is a multiple of any natural number. You know, design or select a natural number, say I, and design the automata. So this is what we had from last time. The automaton M sub 5 that we talked about last time was effectively, it had three symbols, rather four symbols actually. Symbols 0, 1, and 2 were numbers. We treat them as numbers. And then symbol reset was basically a button, for example, that we treated as resetting the sum to 0, which will be a multiple of 3. And then the automaton we had, it would calculate the sum, and it would accept the language, or it would accept the string if the sum of all its elements after the last reset was a multiple of 3. Otherwise, it would reject that string. So I'm just going to go over the definition of this automaton just to give you a quick overview of what it looked like, and then we'll redesign this automaton to basically, and this is your assignment, design or work and generalize M sub 5 to be the automaton M sub 6, which is an infinite automaton whose language is the sum of all symbols in each string be a multiple of I being any number, any natural number. So the automaton will have to have, should be 5 tuple, the Q, sigma, delta, Q sub 0, and F. Q will be the set of its states, its finite set. Sigma is the set of its alphabet, a finite set. Delta is its transition function. We'll define this. Q sub 0 its start state, and F to be its accept states, set of accept states. So in the example that did the module of 3, we had 0, 1, and 2 as Q sub 0, Q sub 1, and Q sub 2 were our set of states. Sigma was reset, 0, 1, and 2, the input symbols. The delta is a transition function, and this example, because it was limited, automaton really had like 3 states. We could list all the states as you see here. The initial state is Q sub 0, and the final state is a set of Q sub 0, or a set composed of Q sub 0, and that was our final our accept state. So using the same four symbols, input symbols 0, 1, 2, and reset, we would like to design this automaton M sub 6. So let's see how we can do this. So we know that our M sub 6 is an automaton that should accept any string in which the sum of all symbols after the last reset is multiple of I, where I is a natural number. So I belongs to n, the set of natural numbers. So I want to design this this automaton to recognize the language of all these strings, as you see here. Now, by looking at this example, I would like you to actually take a very close look at these elements in the definition of the strings that I'm accepting. The definition of the string is basically an arithmetic operation here, the sum of symbols, another arithmetic operation that is a multiple of I. And this is very important as well for us to take a close look at. All the symbols after the last reset. Now, I'm throwing the reset in here just to have some fun with this, but our automaton, if it doesn't have a reset state, then it will calculate the sum of all of its elements so far. So another way to say this is basically to replace this with the phrase so far. And this is at the root of the power of automaton. Remember, the automaton has a very limited amount of memory, and that is at the root of its limitation as well as the power, right? So a finite automaton cannot really memorize the number of things. What it can actually do is to keep a sense of, or rather memorize, things that it has seen so far. So although we will not be able to design an automaton that would be able to calculate, and we will see with later on in the course, what makes a language non-regular, or what makes a language that no finite automata can recognize, is that when your automaton needs to memorize a number of something, and then to account for a number and create an equal number of some other symbols in the string, and be able to memorize, to recognize these, because it will not be able to have an unlimited amount of memory to store all the occurrences of symbols. But what it can do is it can basically keep track of how many of things it has seen so far. So remember, this automata cannot predict when the string is finished, and as a result of that, it will not be able to predict some things that will happen in the future. So your automaton must be ready to accept a string at any given time with the limited amount of memory that it has. And this string of symbols, whose sum of elements is some value, is something that we can actually represent with this limited memory. How are we going to do this? We're going to do this by constructing this automaton. So the first thing, we know that this automaton M sub 6 is basically a 5-tuple. Q, sigma, delta, Q sub 0, and F. Okay, so the easiest part is, first off, let me write Q here. I need to define Q, so I don't know yet. The easiest part is my sigma. Sigma is basically the alphabet, which is reset 0, 1, and 2. I'm designing this automaton to accept only these alphabets, these symbols from my alphabet, which is fine. Then delta will be my transition function, which I'll know is from Q cross sigma over Q. And I need to design my Q sub 0. I don't know what it is, and I need to design and find out what my final states will be. Remember, this is a set, and this is a state. This is a set of states. F is a set of states. Q sub 0 is a set. Okay, so we'll go formally showing you how to design this, but I'm going to just write this automaton as we go by, and then we'll see if this is the correct representation of my automaton here. So what I'm going to do is that I'm going to basically make the set Q to be the set of I states, Q sub 0, Q sub 1, Q sub 2, all the way to Q sub I minus 1. Okay. Now, what would each of these states represent? I'll tell you now, and I'll show you a little later, that each of these states would represent the modulo of the sum of elements seen so far of I. So each of the states, Q sub, if I tell you if my machine is in Q sub I, what does that, or Q sub K, what does that mean? Then that Q sub K is if K was, if you sum up all the elements you've seen so far, take its modulo of I, and if it's K, then you will be in state Q sub K. Okay, so that's what each Q sub K represents. And then as a result of that, I'm gonna basically make my Q sub 0 to be or the start state to be Q sub 0, meaning that when the elements when the machine starts, it hasn't seen any symbol so far, which means that its sum is 0, and 0 is 0 modulo any I, which is a multiple of sub 0. And since 0 is a multiple of 3, and so is any number whose modulo I is 0, then my final state as a byproduct will be Q sub 0, set of Q sub 0 state. Okay, so this designs my machine. Now the last thing that I need to do is to design is delta. So now I need to design its transition function, delta. Okay. I'm going to try to draw it a little bit here, but then you notice that we really don't need the table here. In fact, we shouldn't use the table. I'm just going to use this table here just for clarifying some of the things. So I've got reset, and I've got number 0, number 1, number 2, and then I have a Q sub 0, a Q sub 1, a Q sub 2, all the way to a Q sub I minus 1. So what I'm going to do is I started with assuming that Q sub 0 is an accept state, and it also is a start state, which means that it represents the sum of the elements so far modulo I. So when I see element number 1, all I need to do is just to add 1 to whatever sum I've seen so far. So Q sub 1 will be representing the state in which the sum of my elements so far has been 1 modulo I, right? Or so far modulo I has been 1. Basically, the remainder of the division of the sum by I is 1. So if I don't add any number, which means that if I see Q sub 0, if I see 0 as the input, I'm going to stay in the same state as I were, right? If I add 1 to it, then I'm going to basically add 1 to the number that I've seen so far, and I'm going to go to that state. So it's going to be q sub 1, 2 is going to be q sub 2. Now here, I'm going to go q sub 1 plus 1, so go q sub 2, go q sub 3, and so on and so forth. So basically what's going to happen is that, so I'm going to represent each of these things as a delta. So the delta of q sub j and 0 is going to be q sub j, right? The delta of q sub j and 1 is going to be q sub j plus 1 mod I, right? Because if you add if you add 1 to the j, you might actually end up going over the states that you've got. So you basically calculate the modulo and go back to the beginning. Delta of q sub j plus 2 is going to be q sub j plus 2 mod I. And finally, or rather q sub j comma 2. And finally, if you are in any q sub j and you see the reset symbol, you reset to q sub 0. Okay, which means that all of these are going to be q sub 0. Q sub 0, q sub 0, da da da, q sub 0. This is going to be mod I actually. So then how does this machine look like? It's going to look something like this. You start with q sub 0, which is also an accept state for you. I'm just going to draw a circle around it. Okay. If you see a 0 or a reset, you're going to stay here. If you see a 1, you're going to go to q sub 1. Okay. Now in q sub 1, if you see a reset, you're going to go back to q sub 0. And also, if you see I minus 1, the number I minus 1, which if that is in your symbol, you go back to q sub 1. And then if you see 1 here, you go to q sub 2. If you see 2, you go to q sub 3, and so on and so forth. And so so the reason that I won't be able to really draw this is that I don't really have an I, so I don't know what I is, right? So if I was 7, then I would have 6 states, and then I'll be able to draw this example. Actually, in fact, let's actually do this. Let's suppose that I was 5, for example, and let's draw this machine. So if I was 5, then here's how my machine would look like. So that's my q sub 0, and it's going to stay in q sub 0 if the symbol is reset or 0. And of course this is a start state. Then it'll go over 1, it'll go to q sub 1. Oops. And then over 2, it'll go to q sub 2. And remember, my symbols are 0, 1, and 2, and reset. So this is going to go to q sub 2, and this is going to go to q sub 1. Now, if I'm in q sub 1 and I see 1, I'm going to go to q sub 2. And if I see 2, I'm going to go to q sub 1 plus 2 is q sub 3. And Now if in Q sub 2, if I see a 1, I'm going to go to Q sub 3. If I see a 0, actually here on 0 I stay here, and on reset I go back. And then in Q sub 2, if I see a reset I go back. If I see a 1 I go to Q sub 3, and if I see a 2 I go to Q sub 4. Now let's work with Q sub 3. Q sub 3 over, if it sees 1, it goes to Q sub 4. If it sees 0, it stays here. And if it sees reset, I'm going to go back to Q sub 0, and it also, if it sees 2, it's going to go back to Q sub 0, because 2 plus 3 is 5, so its modulo 5, which is my number here, is 0, so it's going to go back to Q sub 0. And finally in Q sub 4, if you see a 0, you stay in it. If you see a 1, you go back to Q sub 0. And also if you see a reset, you go back to Q sub 0. And if you see a 2, you go to Q sub 1. Because 2 plus 4 is 6, and its modulo 5 is 1. And this is the design of your automaton. And remember, all you needed was the delta of Q sub I and each of the elements, and then you calculate it according to this transition table, or transition function rather. And this will be your transition function. Perfect. So again, I'm just going to go over this one more time and explain how I designed this automaton. M sub 6 is an automaton that accepts any string whose sum of elements after the last reset is a multiple of I being a natural number. So all I need to do is to create a set of states from Q sub 0 to Q sub I minus 1. Each of these states would represent the remainder of the sum so far by I. And since the remainder could be 0, 1, 2, 3, all the way to I minus 1, I need Q sub 0, Q sub 1, Q sub 2, all the way to Q sub I minus 1. So this will be my states. The alphabet is reset 0, 1, and 2. The delta function will be from the domain of Q cross sigma onto Q. The start state is Q sub 0, and the final state is the set Q sub 0, which is when the modulo I of the sum is 0, which means that the sum is a multiple of I. And all you need to do in each state, Q sub j, if you read 0, you stay in that state. If you read 1, you go to the state which is the mod of I plus j plus 1 of mod I. So if you're Q sub 0, then you go to Q sub 1. If you're Q sub 1, you go to Q sub 2. If you're Q sub 2, you go to Q sub 3. If you're Q sub 3, you go to Q sub 4. And if you Q sub I minus 1, you go to Q sub 0. With reading number 2, symbol element 2, then you go to Q sub j plus 2 mod I. So if you were in Q sub 0, you go to Q sub 2. If you were in Q sub 1, you go to Q sub 3. If you were in Q sub 2, you go to Q sub 4. If you were in the Q sub I minus 2, you go to Q sub 0. If you were in Q I minus 1, you go to Q1. So it's kind of like a circular pattern. And as you see, this is the power of the automaton here. And regardless of which state you're in, if you see reset, you go to Q sub 0. You reset to 0. And that will be your finite automaton. Fun, isn't it? Well, seeing this and hopefully understanding this concept, we will now move into the phase of formally defining computation. And here you exactly saw a informal way of representing the computation of calculating modulo, or the operation modulo. So so with this, I am going to close out this this video in the list in this unit, and now immediately after this video, we will start working on formally defining what what computation means.